I want to find the derivative of f of x equals natural, that's not natural, that's log base 2 of 3x. And I'm going to be using this derivative rule here, where the derivative of log base b of u is u prime over u natural log of b. And that b is the base. So to find the derivative of this, we still need to do the derivative of the inside over the inside, but we need to multiply by natural log of the base because that base is something other than e. The derivative of 3x is 3, and we can see that these 3's cancel each other out, giving 1 over x natural log 2. As our derivative. I'm going to show you this example in a slightly different way, and this one involves doing a little bit of algebra before we take the derivative. So we have our function log base 2 of 3x. Now, there is a property of logarithms called the change of base formula, and it allows you to rewrite the log with any base of your choosing. So I'm going to rewrite it with natural logs since that's what the most common derivative formula uses. So the change of base formula would have us rewrite this as natural log of 3x over natural log of 2. So what's inside the log goes inside the natural log in the numerator, and the base of the log goes what's inside the natural log in the denominator. Now, once it's rewritten in this form, you would consider 1 over natural log of 2 to just be a constant because there's no variable in there. So this is the same thing as 1 over natural log 2 of 3x. And now when we calculate the derivative, the 1 over natural log of 2 is a constant multiple, which you would carry down. And you're going to apply the derivative on this part here, the natural log of 3x. And the derivative of natural log is u prime over u. So that's the inside derivative over the inside. So we're going to get 1 over natural log 2 times the derivative of 3x is 3 over 3x, and then those 3's cancel each other out, and we have 1 over x natural log 2 as our derivative. So we get the same answer if we do a little bit of algebra first. For this question, we want to find the limit as x approaches -2 from above of the greatest integer less than or equal to x plus 5. So when finding the limit with greatest integer functions, there are changes at every integer because of it being the greatest integer function. So if I do direct substitution on this, I'm going to get, I might not get the right answer. So what I want to do is a slightly modified version of direct substitution by making sure that I choose, instead of an integer, I want to choose a number that's close to that integer, but making sure I still follow the rule that was given. We want x to approach -2 from above, so I'm going to choose something that's close to -2 and above -2. So I'm going to write out my number line because negatives are always opposite than positive, so I want to make sure I get it right. So my integer that I'm working with is right here at -2, and I want to make sure I choose a number that is above -2, So I would choose something like negative 0.5. So let's substitute negative 1.5. Let's choose negative 1.5 to substitute in to the greatest integer function of x plus 5. That would give me 5 minus 1.5. That would be 3.5. The greatest, and that should be negative. No, that's positive, sorry. We want the greatest integer less than or equal to 3.5, and that would be 3. So this limit will approach 3. In this question, we're finding the limit as x approaches infinity of 1 minus x over 3x squared minus 7x plus 4. So if I use direct substitution right now, I'm going to get some version of infinity over infinity, or negative infinity over infinity, or infinity over negative infinity, or negative infinity over negative infinity. If any of these forms come up, we know we're going to be able to do a little bit of simplification to try to find this limit. So the simplification that we're going to do is going to be to take the highest power from the denominator, and we're going to divide that into both the numerator and the denominator. I'm dividing x squared into the numerator and dividing 3x squared minus 7x plus 4 by x squared as well. Now what this does for us, it's going to create a situation where our denominator is kind of quote unquote heavier than the numerator. So what that does for us, anytime we have the limit as x approaches infinity of 1 over x, our denominator becomes heavier than our numerator, then this limit is going to approach 0. So by dividing by this x squared, we're pulling some of that weight into the denominator and hoping that we're going to be able to find some limits going to 0 instead of all the infinities that we have previously when we did direct substitution. So if we simplify, we're going to get the limit as x approaches infinity of 1 over x squared minus x over x squared. And in the denominator we have 3 over x squared, 3x squared over x squared minus 7x over x squared plus 4 over x squared. Some of these fractions simplify. 1 over x squared. Then we have x canceling with an x in the denominator to get 1 over x. And then x squareds cancel to give me 3. And then we have an x canceling here, giving me 7 over x minus 7 over x plus 4 over x squared. So now when we apply the direct substitution method, we have 1 over infinity squared minus 1 over infinity over 3 minus 7 over infinity plus 4 over infinity squared. So all of these fit what I was talking about here, where the denominator's going to infinity and the numerator's fixed. So our limit of those fractions will approach 0. So we have 0 minus 0 over 3 minus 0 plus 0. That's 0 over 3, which is 0. So this limit is approaching 0. And then in previous classes, we've studied these types of functions. These are called rational functions. And when we're looking at the limit at infinity, we can bring horizontal asymptotes into the discussion. So if we look at it from that perspective, we would look at the degree of the numerator. The degree of the numerator would be 1. The degree of the denominator is 2. And because the degree of my numerator is less than the degree of my denominator, I know that this function has a horizontal asymptote at y equals 0. And that is exactly where our limit at infinity came out to be. In fact, the definition of horizontal asymptotes is the limit as x approaches infinity.
So those coincide with each other.